Okay, here we are at week 8 already, and we're looking today at the intersection of 3 planes. It's our last little look at at how planes and lines and vectors interact with each other. So just got a little graphic off it to the right here because it becomes quite challenging to draw 3 planes. So I'm drawing a little help here from Google Images, and we've pretty much got all the cases covered here. Okay, so you can see if we go through them one by one, then this diagram here shows three planes intersecting at a single point. So this is intersecting at a single point. So that's one of the possible outcomes when 3 planes meet. Now, if you're just looking at 3 random planes, then really it's most likely that they'll be like this case here, or they'll do this, and that is that they won't be a common point of intersection at all. Right, 3 parallel planes obviously is a fairly unlikely event, but obviously no point of intersection there. So in these 3 examples here, there is no intersection, and they present themselves in different ways when you're looking to find common points. So we'd say here that there's no point of intersection. No point of intersection. And that's the same with here, where we've got 2 planes that are. Here we've got 2 planes. Oh, sorry, I'm trying to write and talk. It's always a bit difficult for me. 2 planes that are parallel and 3 planes that are parallel. No points of intersection. Now, sometimes when we establish that there's no point of intersection, then we might go a little further and just try and establish whether we've got parallel planes, and that's just simply a matter of looking at the normal vectors to those planes, and from the coefficients of x, y, and z. So you might even look at this particular example straight away, where we've got 1, 1, 3, negative 1, 2, 2, 4, 1, negative 3. You can see that none of those are in any way related, so there's no parallelness going on. So we can rule out these 2 possibilities that we've just looked at for this particular set of equations. So they're either going to intersect at a single point, they're going to have no point of intersection like this one here, or in this example where they're going to intersect, if you can see here, they all intersect like this. These are like the pages of a book that have just been opened up, and they intersect in a line. So there's an infinite number of points of intersection, or we could just say that they intersect in a line, and we can define that line in all the ways that we know how to define lines through this course so far. Okay, so there are our possibilities. Let's do an example. So what we're going to do here is we've got 3 equations and 3 unknowns, three plane equations, and we're going to go looking for a point of intersection. So we proceed as we would normally in such things, and we look to eliminate variables. So what we tend to do is we pick on a variable and decide, right, we're going to get rid of it. It looks like the most vulnerable, the one that I can remove most easily, and I'll do that in 2 pairs of equations. So I'll be left with a pair of equations in 2 variables. So we just narrow it down and go from there. So let's get to work. I would suggest that maybe from 1 and 2, you might see that x looks as if it can disappear quite simply. So we might say that our goal, or our strategy here, is to remove x. So we're going to eliminate x, right? Eliminate. So you choose. So step 1, perhaps if we formalize it a little bit, I might write step 1. So choose a variable. Choose a variable to eliminate. And then eliminate it. So then we go to work on it in 2 pairs of equations. So choose a variable to eliminate. So in our case, that's x. So we're going to say 1 plus 2. 1 plus 2. I want to see what that gives us. I know I'm going to get rid of my x. I'm going to end up with 3y plus 5z is equal to 8. That looks reasonable. I'll call that equation 4. Now, I'm now going to pick another pair of equations and eliminate x. There's no point me going to another variable because I'm just making things complicated. So if I go to what could I do here? I could take 2, multiply it by 4, and add to 3. Does that look sensible? So I could take 2. So I could take 4 times equation 2, and then add it to equation 3. So I just use another pair of equations. There are 3 pairs, 3 options, aren't there? 1, 2, 1, 3, 2, 3. So I pick 2 of those 3 pairs to eliminate the same variable. So I've taken 4 times 2 and I'm adding 3. So that means that my x's disappear. I end up with 8y, and my adding s plus 1 is 9y. I end up with 8z minus 3z is minus 5z. And I end up with 4 3s are 12 plus 2 is 14. And I'll call that equation 5. Okay, just spotted an error here. This coefficient of z, 4 times equation 2 gives me 8z, add negative 3z. And I've got positive 5z, haven't I? So that's a plus just there, plus 5z. Alright, so now I've got 4 and 5. It looks like I can do a subtraction here, and I might say from those, I might say equation 5 minus equation 4. So I end up with 6y, 5z minus 5z, 14 minus 8 is 6. So 6y is 6, y is 1. Okay, so if y is 1, therefore I get 3 times 1 is 3. Looks like z is equal to 1. And if y and z are both 1, I can go back up to equation 1, and I can say that x plus 1 plus 3 is equal to 5. So x plus 4 is 5, and therefore x is equal to 1. So therefore, I do have a unique point of intersection. And that is the point 1, 1, 1. Right, so I've used Geogebra to graph these 3 planes, and perhaps you can see here the point of intersection in there at 1, 1, 1, single point of intersection of those 3 planes magically. Okay, so that's example 1, and so you can see what's happened there. We're going to proceed in exactly the same way because we don't know going into an equation what the nature of the relationship between the planes will be. So we just proceed to solve, and then we deal with what comes up in front of us. Now in this one, you can see that everything rolled out pretty nicely. There were no strange occurrences. We're going to see now. So that really, I've chosen step 1, choose a variable to eliminate. Once we got to that stage, step 2 was then solve for the other 2 variables, wasn't it? So I could have popped that little step in here. So what I did there was eliminate those 2 variables. So underneath that, step 2 was solve the resulting 2 by 2. When I say 2 by 2, I'm talking about 2 equations in 2 unknowns, 2 variables, simultaneous. Solve the resulting 2 by 2 simultaneous equations. Now in this case, step 2 just happened, right? We solved for y and z, and then we subbed back in to get x. That was fine because that was a unique point of intersection. You'll see that when we get to the next example, we're going to have at this point, it's not going to come out as a unique solution. So that's when we know it's not just going to be a single point. So let's draw up the next example. Right, next equation, find the intersection of the planes. So off we go again. Let's look to eliminate, in this case, is there an obvious candidate? If there's a single variable, so single variable, that's not quite right, is it? If there's a coefficient of 1, so in this case z, then that's usually going to be, there's no other single, so we can always get use z fairly simply to make elimination. So from equation 1, always label your equations so that you can talk about them. So what we might say is, let's take equation 1, multiply it by perhaps 5, and then do a subtraction with equation 2. So I might say, we might say we'll take 5 times equation 1, 5 times equation 1, and then subtract equation 2. If we can do all that in one move without making any errors, that'll be excellent. So 15x, 5 times, I'm just going to do it, one term at a time, 15x minus 7x. So that gives me, the result there is 8x. 5 times equation 1, so that's 10y, I subtract 4y, and I get positive 6y. 5 times z, subtract 5z, that's what I wanted to do, eliminate that z. 5 times 1 is 5, minus 3 is 2. So 8x plus 6y is equal to 2, or I can simplify that to 4x plus 3y is equal to 1, and let's call that equation 4. 4x plus 3y equals 1. Now let's go with, let's multiply equation 1 by 3 this time, and then subtract equation 3. So I'm going to go back, I'm going to go over here and say now 3 times equation 1, and then subtract equation 3, right, using that sort of notation. So I've got 9x now, subtract 5x, gives me 4x. 3 times 6y, subtract 3y is plus 3y. Now z, 3z minus 3z, z's are gone. 3 times equation 1, 3 minus 2 is equal to 1. Call that equation 5. Now you can see here that right now I've got 2 equations. I've got a 2 by 2, 2 equations and 2 unknowns. 4x plus 3y equals 1, 4x plus 3y equals 1. So here's my moment where I realize that I do not have a unique point of intersection. In fact, one step further, I realize that what I have are an infinite number of solutions, because whenever 4x plus 3y equals 1, I've got intersection. So I've got intersection. So that's telling me that I have an infinite number of points of intersection, which is this case right here where the 3 planes meet at a line. So what would happen if there were no points of intersection at this point is that these would be inconsistent equations. I would get 4x plus 3y equals 1, 4x plus 3y equals 2, or something like that. That would tell me that I'm not going to find a point of intersection, inconsistent equations, and they don't have a common point or line or anything. Right, so at this stage, I now go to establishing the equation of my line. So we do that in this way. So my acknowledgement here that I have an infinite number of points of intersection, and they are in the form of a line. Infinite number of points of intersection. Okay, so they meet in a line, like the pages of a book. So that's what I deduce here. Now I'm going to go and find those equations. So what I do in this case now is I will go and I'll make y or x the subject of this consistent equation. So what I'll do is make y the subject of the, I'm going to call it consistent equation, because that's what it is. But what that is to do really is to highlight the difference between the next example where this will be inconsistent. Make y the subject of the consistent equation formed. So what we do there is say, okay, so therefore we could have made x the subject, doesn't really matter. So we make y the subject, we get 3y equals 1 minus 4x, or y equals 1 minus 4x over 3. And what we do with that is we substitute it into the third equation, the one that we haven't used. Actually, sorry, we've used it, but I'm going to substitute that into, so I can find out what z is. I can substitute that into any of my 3 equations. So what I want to do now is I want to find out what z is in terms of x. So now I want to establish my z in terms of x. Now you understand that at this stage I could have made x the subject of this, in which case then I'm looking to establish z in terms of y, but I want to get everything in terms of x, and you'll see why in a moment, or in terms of just the one variable. So I've got y as the subject, so I've got y in terms of x. Now I want to get z in terms of x, and I'll get that by substituting this this y into, I'm going to go into equation 1 because that's where I've got singular z. So I can say that z, all right, so from 1, z is equal to 1 minus 3x minus twice this value of y, 1 minus 4x over 3. Y equals 1 minus 4x over 3, so I write that. Now I'm going to get z in terms of x. So I've got z is equal to, I will just work this out, simplify this down. So I end up with minus, so 1 minus 3x, so then it'll be minus, what is it, 2 minus 8x over 3. So that, if you can see that, that runs through as minus 2 plus 8x, which is fine. Then I'll put this all over 3, so I'll end up with 3 minus 9x minus 2 plus 8x. Once that minus runs through these two terms, remember that's considered as a bracket, all over 3. What does this simplify back to? Minus 9x plus 8x, so I end up with minus x plus 1 over 3. Okay, so now I've got z in terms of x, I've got y in terms of x, and I've got x in terms of x. So I'm good to go now. I'm ready to represent my infinite number, my infinite number of points on my line as my point of as my line of intersection, my intersecting points for these three planes. So let's do that. So therefore I can write this as, where shall I go now? So I'll just head up this way, I think. So I'm going to introduce, my third step now is to introduce a parameter. So introduce parameter lambda, for instance, seems to be popular. Now this is so that I can write my line equation as my parametric equation. So I'm going to get my x, y, z parametric equations for my line of intersection. So I'm going to, whatever I've made everything else in terms of, that's going to be defined as my parameter. So x equals lambda. I can therefore say that y equals 1 minus 4 lambda over 3, and z is equal to, what's that say, minus lambda, or 1 minus lambda over 3. So now we want to write this. These are my parametric equations for this line of intersection. I might want to write this in Cartesian form. In order to do that, I'd like to see what lambda equals to. So I can see quite clearly that lambda equals x here. That lambda equals, what is that? 3y minus 1 over negative 4. That seems reasonable. And then over here, I've got lambda equal to 3z minus 1 over negative 1. I hope I've got that right. So they're my lambdas. So now I can write in Cartesian form. In Cartesian form, I can write that x is equal to 3y minus 1 on negative, well, I wouldn't write it like that, would I? I'd write it as x equals, I wouldn't have negative 4 under here, I'd multiply through by negative 1. So I'd have, what would I have at the top? I'd have 1 minus 3y over 4, and I'd do the same here, and I'd have 1 minus 3z. That's an equal sign there. And my writing has gone to pot, 1 minus 3z here. So they're my equations in Cartesian, that's the equation of this line in Cartesian form. Now perhaps we want to write it in vector form. So yeah, in vector form. So I want to write the vector equation of this line. In vector form, I would want to see this now as, well, I need to see what direction it's going in. I need to see a position vector. So I'd rewrite this as x, I'd go, right, x minus 0 over 1 equals, I'd reorganize this to, what would I do? 1 minus 3y over 4. That's not much good to me. I need to change this around. So that'd be, firstly, I've got to let's do it in 2 stages maybe. So it'd be 3y minus 1 over negative 4. And this one here would be 3z minus 1 over negative 1. And then I'd have to have another go at it. Therefore, x minus 0 over 1. I'd need to divide through by 3 now. So it'd be y minus 1/3 over negative 4/3, and I'd divide through by 3 here, so I'd get z minus 1/3 over negative 1/3. Now from that we could write that my vector equation, which is r, which is x, y, z, is equal to my position vector is across my numerators, so it'd be 0, 1/3, 1/3, and I would have, there's my parameter lambda, and my direction vector is underneath there in my denominator 1, negative 4/3, negative 1/3, negative 4/3, negative 1/3, which could just come back to, just so it's a bit nicer to read, 0, 1/3, 1/3 as a position vector. And then lambda, we could multiply through by 3 here to get 3, negative 4, negative 1. Okay, so that is a vector equation for the line of intersection. Now, Geogebra has done the work for me here. There are the 3 planes defined by 1, 2, and 3 up here. And you can see them there intersecting in a line that is defined in vector form, in Cartesian form, and in parametric form. So a fairly comprehensive solution to that equation. Let's do one more example. And in this example, we'll see how it all breaks down, and we can recognize that there is no point of intersection. Righto, next example, the intersection of the planes as defined. So let's look to make an elimination. It seems to me as if z might be our operator here. So if I say add 1 to 2, just straight up, so if I take 1 and add to 2, we should be able to eliminate z. So I'll get 4x plus 3y. 4x plus 3y, z's are gone, and I get equal to 4. Now I can use, perhaps I'll multiply 2 by 3 and add to 3 to eliminate z out of 2 and 3. So I'll take 3 times equation 2 and add to equation 3. And I'll get 8x, 3 times y plus 3y, so that gives me 6y. 3 times negative z plus 3z gone. 3 times 3 is 9. Add to 2 to get 11. So I get 8x plus 3y, so 4x plus 3y equals 4, and 8x plus 6y equals 11. So this I can rewrite as 4x plus 3y is equal to, what have I divided by? 11 over 2. Now, this is what at the last stage, all right, so if we go back to the last 2 examples, at the first stage, when we got to this point, we just solved and we had a unique point. And in the second example, we got to this stage and we noticed a consistent pair of equations. Now, what we see, 4x plus 3y equals 4, 4x plus 3y equals 11 over 2. What we see are an inconsistent pair of equations. So we have no point of intersection here. I'm just looking for, right, so what I have here are an inconsistent equations, inconsistent pair of equations. So therefore we have no solution. So therefore no intersection. There's no intersection point, no intersection line, no intersection anything. These planes do not meet. So they're just to highlight that we have an inconsistent pair of equations, and that those that there's no. So the point here is that we have 4x plus 3y and 4x plus 3y equals 4 equals 11 over 2. So clearly that if we solved here, we would get 0 equals to 3 over 2 or something like that. So clearly that's nonsense, no point of intersection. Whereas if that is the same equation, then they're consistent, and we can go ahead and find the parametric equations, and we can get the equation. It'll be an infinite number of points of intersection, i.e. intersecting in a line, and we can get that line equation in whatever form we need to. Okay, and here are our 3 planes as graphed by Geogebra, and so you can see how there's intersections, but there's the three planes don't intersect at a common point. We've got this plane here that's intersecting those two, and these two intersect. So in pairs they intersect, but as a trio of planes, there are no points in common. Okay, exercise 11R awaits, and I think questions 1 to 6 will be good to do.